All right, so here's a quick review of the concepts we've covered this unit. We're talking about work, energy, and power. And the first thing we talked about was the fact that work is the transfer of energy, or the ability to do something for you, like to apply a force over a distance. And so if you know the force that is exerted and you know the distance that it moves an object, you can find the work done, which is the force times the distance. The things you got to remember here is that the work is positive if energy is gained. So for example, if I push on a box and it moves faster, then it gained kinetic energy, the work is positive, and the work is negative if energy is lost. And in general, if the force and the displacement are going in the same direction, you will add energy to your system. If they're going in opposite directions, for example, if something is falling, the air resistance force is up, it's moving down, then the work will be negative. So that's how you calculate the work. And remember, the work, the easiest way to think of it is it's the energy transferred. All right? The second thing we talked about was how to find a couple of energies. The kinetic energy was the energy of motion. It was 1/2 of the mass times the velocity squared. If the mass was in kilograms and the velocity was in meters per second, then the energy was in joules. We talked about potential energy of various forms. The kind we are interested in right now is potential energy due to gravity. And in that case, it's found by m times g times h, where height is how far you are above or below a reference line. So potential energy is relative, and when you're solving a problem, you've got to make sure you indicate clearly what it's relative to. We talked about all kinds of other forms of energy, but for our calculations, the third one we talked about here was the mechanical energy. And the mechanical energy is energy of position and motion. So for our purposes, the mechanical energy is equal to the kinetic energy plus the potential energy. So those were the building blocks for this unit. Those were the things that we figured out. Kinetic energy, energy of motion, potential energy, energy due to position, mechanical energy, which is your motion energy and your position energy together. And of course, the work, which is the energy transferred from one form to another, is the force times the distance. Okay? Kinetic energy can never be negative because velocity can be negative, but when it's squared, it's positive. Mass can never be negative, so kinetic energy is always positive. But potential energy can be negative if you are below your reference point. And work can be negative if energy is transferred out of your system. Okay? So that led us to what is really just the big idea for the unit. And the big idea for the unit is that the mechanical energy you have at the end of a process will be equal to the mechanical energy you have at the beginning of the process, plus any energy which is transferred into or out of your system. Okay? So we solved a bunch of example problems, but the idea is, for example, let's do a little example problem here to make sure we understand. If I have a roller coaster and I want to know at the tippy top of the roller coaster, which happens to be, let's say, 18 meters above the ground, my roller coaster is moving at 3.0 meters per second. How fast will it be going when it reaches the ground? Okay? So that's an application of this idea here. This is called the Work-Energy Theorem. So what we have here is mechanical energy. It's moving and it's above the ground. So it has potential energy and kinetic energy. When it gets down to the bottom here, it has no more potential energy. It is just kinetic energy. And the Work-Energy Theorem says the energy we have here will be the same as the energy we have there. So what we can do is we can say the mechanical energy at the end, so that's down here when the roller coaster is down here, will equal the mechanical energy we had at the beginning plus any energy that's transferred into or out of the system. And one of the key words you have to know, if we say that mechanical energy is conserved, that means the work is 0. There is no energy transferred into or out of the system. We don't lose any energy due to friction. We don't add any energy due to pulleys or rocket engines or chains that make you go faster or anything like that. So then what you do is you then apply this big idea. At the end, we have only kinetic energy. So that's 1/2 mv final squared. We don't have any potential. At the beginning, we had potential, so that's mgh initial, plus it was moving. So we have 1/2 mv initial squared. And so applying the work-energy theorem to this problem gives us an equation, and then you can do whatever you need to do with the equation. In this case, I asked you to solve for v final, how fast it's going at the bottom. So you can solve this equation for v final. And a quick note, if every single term has an m in it, you can factor it out and it will cancel. So even though you don't know the mass of the cart, in this problem it doesn't matter. Be careful, that doesn't always happen, especially if there's work, because work doesn't have an m in it sometimes. So you can solve this equation for v final and find out how fast the cart is going at the bottom. Okay? The last thing we did in this unit is we defined the power. And so the other equation here is that the power is equal to the energy transfer divided by the time. The units of power are the joule. And so the joule is the unit of energy. And so power is measured in units of energy divided by units of time. So if you want to find the power, the rate that energy is transferred, you've got to find the work that is done, and you've got to divide it by the time that it takes to do the work. So the last homework assignment has a bunch of problems to review these ideas, a couple with the building blocks, those are fairly simple, and then mostly with the work-energy theorem and some problems involving power. Okay? A couple reminders about power. The units for power are watts. A watt is equal to a joule per second. And there were some conversions. The common one is to use horsepower. So sometimes we give the power in horsepower. And we've put that in our toolbox before, how many horsepower, how to convert horsepower to joules. So that's a quick review of what you should be able to do and know for this test. There's no conceptual part on this test, just a problem-solving part coming up. But you got to be able to apply the work-energy theorem to be able to solve for maybe the height of the hill or the mass. And the review assignment has some practice problems for you there.